Today I will explain the paper Contrastive Learning, Visual Attention for Multilabel Classification. And in my opinion, this paper is very important because it followed the huge momentum we have seen in computer vision. And this momentum has been driven by applying contrast learning to vision. And we see a lot of progress, for example, in CLIP, by merging cross-modal inputs, for example, text and images, in which you basically build a shared latent space between text and images, so that, for example, you can then one-shot classify your images based on the textual classes you want to classify. But one important limitation of such algorithms is that they operate on a single label image. That is, one image is represented as one single embedding, and this embedding represents just one label. For example, just to give you an idea, in ImageNet we have one label, one class for each image. But in reality, much of the task we want to solve in computer vision, for example, image segmentation or object detection, whatever, have multiple sources, multiple labels. And also the images that we are going through every day has multiple classes. For example, person, they have cars, they have cameras, and so on and so forth. So we need to broaden this contrastive learning paradigm to images with multilabels. And that's exactly what the paper of today do. The algorithm is called MulCon, or multilabel classification with contrastive loss. And they, as explained, basically they adapt the architecture that use a contrastive loss. We deal with images with multiple labels. And the basic architecture is this one. You can see that they have an encoder that encodes the image and produce some visual features. Then we can note two major parts here. One is the class-specific embeddings, and one is the multi-annotation block. The class-specific embedding is just a stack of embeddings that represent the specific class. For example, the first one, I don't know, is bicycle. And it will represent the embedding of a typical bike. For example, this one. I don't know. Okay. For example, this one. The second one represents a car. So we have an embedding representing the average car, I would say, okay? And so here we have the embeddings of all the classes we want to classify. And that multi-annotation block takes as input this list of embeddings and the visual features of the image we are looking at. And for example, our image is this one and contains car and a person. And what this multi-attention block will produce is this label level embedding, and are basically just the embedding of a particular class. For example, this one is the bicycle of the image. Okay, but here we don't have images, so we'll output an arbitrary embedding. But instead, the embeddings corresponding to the car will produce the embedding relative to this car and this car, okay? So we will not have an average, we will not represent the average car as in the class-specific embeddings. Okay, and from this we have two projection heads. One is a classification head. They just project the embeddings, the level embeddings, into probabilities, and then we can just use the usual binary cross entropy loss. and the other is the contrastive loss. But if you just think about it, there's a problem if we just take these embeddings, for example, and use our contrastive loss on top of it. That is, we have some embeddings that are not in the image, so will not produce a real embedding of this instance of an object. So will not provide any useful learning signal. Okay. So what they do is after this projection head on top of the label level embeddings, they mask and take just the embedding that are in the image, because from the image, the images are labeled, so we know what objects are inside it. So after this mask operation, we take just the embeddings that are in the image with a label in the image. For example, these three that we said it represent, well, whatever. And so we can compute the contrastive loss on them so that we can band them together. But the embeddings of the other class are pushed apart, so we can cluster better the embeddings of instances of the same class. And in this way, by leaving alone the embeddings that are not in the image, we can just compute the usual contrastive loss and compare embeddings of the same and different classes. And that's basically it. Here you can see that they have step 1 and step 2, meaning that the training is divided into steps. The first is just the usual cross entropy, in this case is binary cross entropy loss, is optimized, and this basically serves better to pre-train the network and initialize the class-specific embedding properly. And instead, in the second step, basically now the class-specific embeddings are already formed, so that we have more, I would say, specific level embeddings, and then the contrastive loss can more efficiently operate on it, because if you're not well defined the classes of each embedding, then probably the contrastive loss will push apart something that actually makes sense, or it will confuse everything. Okay, so they take these two steps. Now that we take a look at the architecture, we can see some results. But for example, here they trained on MS Coco and NUS Wide, and obviously both of them has multilabel images. But before going to the results, I want to show you here this Disney visualization of the embeddings of the architecture trained just with with the cross entropy loss. And you can see that the cluster between embeddings of same class are not well clusterized. It's very sparse here. You cannot locate maybe this one, but all the other are interconnected with each other. But if we add the contrastive loss, here you can see that the embeddings are clustered together, and obviously here the colors correspond to the different classes. And so that's very very important to see. Okay, going back to the results, you can see here, for example, in MulCon, it outperformed other approaches. But what I think is most important is show you these results, that basically an ablation study of their architecture. You can see that just the architecture outperformed the backbone just trained with binary cross entropy. And that's very, very interesting. Maybe by creating specific embedding for each class, help the network to better differentiate between them, or it's very interesting to see it. Also, without pre-training, it really follow behind with a map that mean average precision of 81.81 compared to the 84. And an important result, but maybe not so important, I will explain why later, is that by introducing the contrastive loss doesn't help so much, like 0.2 points, that it's very low. And why did I say that is not so important? Well, because the strength of this paper is showing that we can adapt the contrastive paradigm to images with multilabels. We don't actually care if it improves the performances. That's because by enabling contrastive loss on multilabels images allows you to use many different training strategies, learning strategies. For example, merging cross-modal learning, that is using both text and images, like we see have done Florence by basically merging clip with this architecture that we are seeing now. So the important part is the architecture, not the actual results, though they are useful. And an important task that you can do if you add a contrast loss on top of the images is basically this one, and is an image retrieval task. For example, here the query is this image, and the class is the apple, so we want apple that correspond to this image. And if we train just with the cross entropy loss, that is without the contrastive loss, we see that the images doesn't make any sense. We ask for apple and we have tie, teddy bear, books, whatever. And also here, for example, we ask for teddy bear, and the algorithm finds that the most closest embeddings come from this image with this class, tie, teddy bear, yes, that's correct. Then we have a cat that doesn't relate with teddy bears, and neither this output. But if we add the contrastive loss, here you can see that everything, almost everything except this one, makes sense. We ask for an apple, and this is an apple. Here the apple, and so on and so forth. Books, here are the books, here. And so you can see that the architecture, the contrastive loss actually help improve the embedding space. So to contrast different embeddings of different classes and make together embeddings of the same class. And now, because they are using a multi-annotation block, we can see the attention maps. For example, if the input is the cow, the label, is the cow, you can see that she's looking at this part and this part that are correct. For the person is looking at this person, though maybe it should have look a little bit above. But here the other person, here. So it's the attention maps is concentrating to the correct part of the image. And that's basically it. I will stress out the importance of this architecture that allows us to then use images with multilabels on every kind of contrastive learning paradigm you want. If you enjoyed this video, let me know, and I will do a review of the paper of Florence. It's really interesting to see how they merge this kind of architecture with the learning strategy that is the cross-modal contrastive loss used in Clip, that is using both images and captions. Okay, see you in the next video. Bye.